Okay, so today we'll be looking at some more methods or some more aspects of paging. So, what was the second problem about paging that we did not discuss till now? So, it was that the page tables are very large. Okay, and that was because the page tables were linear. For example, we had seen that suppose there is a 32-bit address space, then that is 2 to the 32 bytes or 4 GB of address space. And if we have 4 KB pages, that means 2 to the 12 byte pages. Then the number of pages is 2 to the 32 divided by 2 to the 12 is equal to 2 to the 20. And if we take like 4 bytes per page table entry, then the space required for is 4 MB. So this is approximately 4 million, right? Okay. So this is a large value because I mean there can be hundreds of processes. If we keep allotting like 4 MB for all of them, then it's going to be a lot of memory used. Okay. So the question that we'll be addressing today is how to make page tables smaller. Okay. So one simple solution can be just have bigger pages. So suppose instead of 4 KB page, we have 16 KB pages. Okay, so 16 KB is 2 to the 14th. Okay, so now number of pages is equal to 2 to the 18. And now page tables, number of entries in page table to the 18, and suppose 4 bytes per entry. Then this will be 1 MB. 2 to the power 18 times 4, which is 2 to the power 2, which is 2 to the 20. So it will be 1 MB. Okay. So this is a factor 4 reduction. And I mean, this is because we increase the page size by a factor of 4. So the reduction factor we are going to get is same as factor of increase in the page size. So reduction factor in the size of the page table, right? So this is one solution that we can use bigger and bigger pages, and that will reduce the number of entries in the page table and hence the page table size. But can anyone guess what is the problem with this approach? So what can go wrong if we allocate bigger and bigger pages?
The number of processes run.
Number of?
Lesser number of processes will be able to run simultaneously.
Why?
Because number of pages has reduced, and if like you see one process, one page, and then
No. So I mean, okay. So let's see what you're saying with it. So if we have here we have 16 KB pages or even.
okay, so page table virtual memory concept.
Yeah, and I mean the actual physical memory is quite large, so the number of processes is not going to reduce. Like even you have, so here we are just going for 16 KB pages, but even if you have like 1 MB pages, just like, and you have 1 GB space in your memory, then there can be 1024 processes that can run. And generally, the memory space is quite large. And 1 MB is like, so if you have like even 256, then you can have like 4096 processes, which is a large number. So that is not exactly the problem, that the number of processes that is going to run is going to be small.
There will be internal fragmentation more, like more memory is allocated than it is required.
Exactly. So the problem is going to be internal fragmentation. So within each page, there will be wastage. So internal fragmentation. Like, I mean, and why this would happen, that even for small requests, we have to allocate big pages. So memory will fill quickly. And for this reason, the typical page size in most operating systems is kept 4 KB or 8 KB. Okay. So this simple solution, as most simple solutions are, is not really like viable solution. So any other solution that can be achieved? So one way to do this is the hybrid solution. Combine paging and segmentation. Okay. So suppose we have a 16 KB address space. Suppose each of the rows represents 1 KB. So this is 7, this is 15. And suppose the code is here. the heap is here and the stack is here, and everything else is free. Okay. So now if we go for a linear page table, and so suppose 16 KB space, like virtual space, divided into 1 KB pages. Okay. So in that case, in linear page table, you need to have an entry for every page. And then we'll be marking these free pages invalid, right? So that is a waste of space. So now and for unused pages, valid bits will be 0. Okay. But still these unused pages will occupy some space in the page table. And we want to get rid of it. Like we don't want to waste this space in the page table. Okay. So the idea is to make use of base bounds pairs of registers. As we did in segmentation. And then have a separate page table for each of the segments. So now we'll allot one page table to the heap, one page table to the code, one to the stack. And now the page table will have only the pages which are in use in those segments, right? So the base register will point to where should it point to? Now it does not point to the physical addresses, right? So what does it point to now? No. The start of the page table for that segment. Okay, and the bounds register will just hold the size of that table or number of valid entries or number of contiguous, or let's say will hold the size of the page table, which will be like maximum number of a valid entry. So this is how it's going to be. So let's take a small example to understand this. So suppose 32 KB address space, 32 KB address space with 4 KB pages. Sorry, 32 M. Sorry, not 32 KB address space. That's why I got confused. 32-bit address space with 4 KB pages. And let's say we have 4 segments, which are represented by the first 2 bits. Of virtual address. Okay. And out of these, we'll consider only 3, like we did before. Code by 00, heap by 01, and stack is 11. Okay. So now the virtual address has these 32 bits. So from 0 to 31. And these last 2 bits will determine the segment. And then, so we have 4 KB pages, so 12 bits are going to be the offset. And the remaining is going to be the VPN. Okay. So this is going to be the idea that now the page table for the code heap and stack, they will separately contain the VPNs for that particular segment. Right. So we'll have 3 base bound pairs. Each for the code heap and segment. And as expected, the OS will need to change all 3 pairs on context switch. Okay. And so what happens in case of a TLB miss? The hardware first extracts the segment number. Okay. So which will determine which base bound pair to use. Okay. And then go to that page table. Pointed by base register. For that segment. Okay. and find correct page table entry, add offset to get physical limits. So so simply what it can be is that the segment number can be virtual address and segment mask, and this has to be shifted. Or segment shift. So basically what this means is that this is going to be 1 1 followed by all zeros, and then you shift it by 30 bits in this case. The VPN is going to be virtual address and VPN mask. Again, VPN shift. So what is going to be the VPN mask here? 0 0 followed by 14, 32, 18, 18 ones and remaining zeros. So that is going to be, and the VPN shift is going to be 12 because you'll have to shift it 12 bits to get it to the right. And then the page table entry address is going to be base register, which base register? The segment number plus VPN times size of the page table entry. Okay. And after this, like we check with the bounce register. So as we said that, yeah, is there a question? No. Maybe just somebody's mic is unmuted. All right. So yeah, so as we said, the bounce register hold the maximum page number that is valid in that page table. So in this case, the example that we were having, now the code page table will have only one entry. The heap page table will have only one entry, and the stack page table will have only two entries. Right? So yeah, and in case of like, for example, if there are three pages, like 0, 1, 2 are pages, then bounce register will have 2. Okay. And now if memory access is beyond the number in bounce register or the VPN, that means, then we can give a seg fault. Okay, and this, as we saw, saves space. So no space needed. In page table for free space between heap and stack. But even this approach has some problems. So let's guess what can be the problems with this approach. So first is that internal segmentation can still happen. Why? Because now we take the heap, and so suppose the heap is sparsely populated. But suppose the first, so suppose this is the heap, and the first and the last frames have been are valid, and everything else is invalid. So still we need, but has like data at arbitrary spaces. So even in that case, the page table can be large. Okay. So this is one problem. And then there is another problem, which is that is of external fragmentation. And why that can occur, even though we are dealing with pages. The last thing should give you one hint about that. Why would external fragmentation happen in this case?
Because we're dealing with segments.
Kind of, but even then the pages are of fixed size, which are being allotted to the segments. But I mean, yes, we are dealing with segments. That's why external fragmentation will happen, but a bit more specific answer to that. Even so, what happens? So the page tables are of variable size. So they also need to be stored in the memory, right? So earlier the page table was of fixed size, which was just determined by how much big the address space is and how big are the pages. But now the page tables are of arbitrary size, and they also need to be stored in the memory. So finding space for them can be difficult. And might lead to external fragmentation. Is that clear why this can lead to a external fragmentation? Okay. I hope nobody's asking. So these are the problems with the segment approach. So another solution that has been looked at is called multi-level page table. Yeah. So here we don't use segmentation. but still we want to get rid of the invalid entries. All, or let's say, or majority of. In the page table. Okay? And the approach is going to be that we chop the page table into page size units itself. So, so the page table is one entity which requires some space and it can grow large. So what we do, we also chop up the page table into page size entries. Okay. Not entries. Entries is used for something else. So sorry for overloading the term. Now, and then if one entire page of the page table does not have any valid entries, then we don't store it in memory. Okay. So this is what we are going to do. We are going to just divide the page table into pages. And then if one page of the page table does not have any valid entries, then we are not going to store it. Okay. But now we need some additional tracking that, okay, which page of the page table does not have uh, any valid entry or which one has valid entries and so on. So to track whether a page of the page table has any valid entries or not, or if it has, where is the page? Use another similar structure. Structure named page directory. Okay. So what will page directory do? So on one hand, it will just keep the addresses of the where the pages of the page table are. Or tells that there are no valid entries in a page. Okay. So this is the like job of the page directory. So let's see it as an example. So with an example, so suppose we had a linear page table earlier, and So suppose it was chopped into like 4 pages. So these are the 4 pages, and this, so this is a linear page table. So this was what was the case earlier. So it would have, okay, let me extend it a bit to have, all right. So, and now the page table based register, as we had seen, it points to the start of this page table. And suppose this was stored in physical frame number 201, this was stored in physical frame number 202, 203, and 204. And let's say these are the valid bits, these are the protection bits, and these are the physical frame numbers. And it is, of course, indexed by the VPN. So suppose the first virtual page is valid. Suppose it's a code one. So let's say read, execute, and it is at PFN 12. This is also valid. Read, execute, PFN 13. This is 0, so does not matter. Then again 1, read, write. So suppose this is a heap and this goes to 100. And then suppose all these are zeros. So these pages are not valid. These entries are not valid. And then finally we have like 0, 0. So suppose this is for the stack. 1, 1. Read, write, whatever, 26, 10. These are the physical frame number where it is residing. So now in case of the this multi-level page table, what we are going to have is now there is going to be one. So this is the page directory. So this is going to have one bit, the valid bit, and physical frame number. And now instead of the this page table based register, we are going to have a similar register, which we are going to call page directly based register. So here it pointed to, so let's say it had the address 201, the starting address of the frame number, right? So now in this case, the PDBR will have the first address of the physical frame of the page directory, and suppose this is 200 in this case. So it will point to the first entry. And now these 4 entries which were there, out of which only 2 are going to be valid here, which have some value. And then this is going to have 201, this is going to have 204, and remaining are going to be 0. And now this 201 will point to this frame. The 201 frame. Which is the same as the linear page table. So 1, read execute 12, 1, read execute 13, 0, 1, read write 100, and then this entry will point to another page, which is at 204. Sorry, so this should point slightly up, not so down. So this is 204, and this is again the same things that were there linear page table. So 0, 0, 1, read write 26, 1, read write 10. Okay, and these 2 pages will not be assigned. So at least the idea is clear. What is going on here? Yeah. So the page directory, as we saw, so this page directory contains one entry per page of the of page table. Okay, and we call it page directory entry. Very imaginative. Okay, and what it contains would contain two things. PFN and the valid bit. And what does this valid bit represent? So this is slightly different from the valid bit of the page table entry. So if valid bit is 0, that means the like rest of the entry does not matter. Or all the pages, all the entries in the corresponding page table chunk are invalid. And if it is 1, then what does it mean? That at least one entry in the page pointed by the PFN is valid. Okay. So this one entry is actually a page of the like process. Okay. So this is what it does, the page directory. So it has like these two bits, as you saw here. It was 1 or 0 here, and the 0 ones don't matter, and the 1 ones point to the corresponding fields. Okay, I hope that is clear. Any questions till now?
So what keeps track of like which physical frame number is allocated or not? Like suppose we ask for a new page, so like which physical frame number would it give us?
No, so physical frame number again, the OS needs to maintain a free list.
Okay.
Yeah, so OS always maintains a free list, and whenever some need arises, then a physical frame number is assigned for that, and then accordingly the page table and the page directly will be updated.
Okay. Got it.
So OS needs to do its free space management anyway. It needs to have the free list of the frames which are not allocated. Okay. So what are the advantages of this approach? First, space saving. for sparse address spaces. Right. So, in fact, like it will use like space kind of proportional. So space for page table proportional to the amount of address space being used. Like in the previous case, we saw that since these two were not being used by the process, all these pages, then we did not assign any memory for the page table for it. Okay. And the second is, so if managed well, the page table can be neatly divided into pages. So to grow the page table, the OS can grab a page from the free list. So it can grab any page, right? So earlier, what used to happen that the whole page table needs to be at one place. So contiguous memory was needed. But now what happened? So in multi-level page table, the page table, different parts of the page table can be at different locations in the memory. Okay. And this becomes possible because of, so there is a technique, there is a name for this technique. So because of indirection, that you are doing this indirectly, the indexing. So sometimes not doing things directly might help. It might give you more flexibility into things. Okay. All right. So what are the disadvantages of this technique? At least one obvious one you should get.
So there are more memory accesses in case of a TLB miss.
Exactly. So for every TLB miss, now we have two additional memory accesses instead of one in case of linear question. So this is an example of what is called space-time trade-off. that we are saving space, but we now the TLB miss will take uh, more time. It will take more memory access, right? So space-time trade-off means like reduce space by taking more time, or vice versa. Another problem with this approach is that it makes things quite complex, right? So whoever, like the hardware or OS handles the TLB miss, will have to do like more complicated job. And this is also one feature that happens many times, that you know we introduce complexity to get efficiency. Good. Okay, so let's just see this like in a bit more not detail, but how does it look like now? So in terms of the, so earlier what used to happen, that the virtual address, so suppose this was the virtual address. So this used to be divided between the offset and VPN, right? And this VPN worked as the page table index, right? And now, how will it look like? Now there will be offset. Then the VPN now will get divided into two parts. So this was VPN. And now this will get divided into two parts. So first we'll give the page directory index. And then the next one will give the page table index. Okay. So I mean, in case of segmentation, we just had 2 bits for that would represent the like, but yeah, this is just a like more generalized version of that concept. And there are a few key differences, but okay. So this is a 2-level page table. Okay, good. So, I mean, so what is going to be the control flow now in case of a TLB miss or for address reference? So first, so suppose a memory reference has come. So first, like the um, hardware will first look for the uh, VPN to be there in the TLB, and if the TLB has, then the TLB hit part remains the same. Like last lecture. And now suppose a TLB miss happens, right? So Like, so this was the else part, which was TLB miss. And let's see what happens in this case. I mean, we have outlined it. Just a moment. Yeah, sorry. So else, which is a TLB miss, what do we do in that case? We have the first find the page directory index, and that is going to be VPN and let's say page directory index mask, and then you shift it by shift value. So here in this case, this mask is going to be these bits to be 1 here followed by all zeros. Okay. Then you extract the page directory entry address is equal to the page directly base register plus PD index times size of the page directory entry. Okay. Then page directory entry is access memory page directory entry address. And okay, and now we have fetched this, and then we just check if it is valid. False, exception. And if not, then now we want to calculate the page table index. And that is going to be VPN and page table index mask. And then you shift it by some shift. So here the page table index mask is going to be these bits to be 1 and remaining to be 0. And then you find the and then you want the page table entry address, and that is going to be just the page directory entry. You extract the physical frame number from it, then you shift it, you left shift it, and then you or with the or you add the page table index times the size of page table entry. And then now you can access the memory. So page table entry. So now you finally get the page table entry by accessing this memory. and then you perform whatever you performed earlier. So if PTE dot valid is false, then you raise some exception. Now, if can access PT protection false, then you raise some other exception. Protection exception. And else if, or sorry, this was else if, this was else. And finally, if these things are fine, then you just do a TLB insert. And in the TLB, you insert VPN, pt dot pfn, pt dot protection loops. So observe that in the we did not change anything in the architecture of the TLB. That remains the same. And then what do? We retry the instruction. Yeah. So this is the control flow. So okay, this is too small maybe. Yeah, okay. So you see that there are these two memory references now. And this is in addition to the the actual instruction that will fetch some memory. So this is the drawback with this approach, so to say. And so the book has a working example, so you can take that as a homework, non graded or something. Read detailed examples from the book. So I mean, but I hope the overall control flow is clear of this thing. Okay. Any questions about this algorithm? So first you extract the page directory index, this part. Then this will give you, and you have the base register that points to the base directory. Then using this index, you go to that entry of the page directory. Now in uh, using that entry, now you go to that chunk of the page table. You use that physical frame number to go to that chunk of the page table, and then in that page table, this part is going to have the index. This part will give you the index in that page table, the second part. And now that index will point to that will have the physical frame number of the page that you're looking for. Now you extract that, and then you add the offset to get the actual physical address. Okay, so let's now quickly also discuss some more things. So one thing is that maybe a page table requires more than two levels. Okay. So here we were talking about the page directory and so on, but what if the page directory itself is big? Okay. should write it down. So basically, we want the whole page table to be divided into like these page size chunks. And if the page directory itself is not like getting divided into pages, or it is not fitting in one page, then that defeats the purpose. Then the whole problem of external fragmentation will come again, because then where we will allot the space for the page directory and so on, right? So for example, let's say that suppose we have a small page is 512 bytes. Okay, so 512 bytes is 9 bits. This is going to be the offset, right? And suppose we have 30-bit address space. Okay, so that will have 21 bits of BPN. So let's see. So now we have this 30-bit address space from 0 to 0 to 29. Okay, and the first 9 bits are, this is the 8th bit, let's say. So this is the offset. And now so since the page is 512 bytes, let's say that suppose a page table entry is 4 bytes. So how many entries will a page table chunk have? One page of page table. Yeah, anyone? Is everyone asleep or what? So we have the size of the page, and we have that one entry takes 4 bytes. So how many entries will be there? We have 512 byte page. We have 4 bytes for one entry. So how many? Okay, 128. I don't know. This is 512 divided by 4. Okay. All right. So the number of entries in one page of page table are going to be 128. So this will take 7 bits for the page table index. Okay. There are these 128 entries. So indexing them will take 7 bits. So let's take 7 bits more for page table index. So now we have come to, let's say, so 9 and 7, 16 bits, right? So this is 15. Okay. And now how much is left? Now we are left with 14 bits. Right? So how many entries the page directory is going to have? Right? So 14 bits, which is going to be 2 to the 14 entries, and let's say 4 bytes each. So the total size is 2 to the 16 bytes. Right? And what is the page size? Page size is just 2 to the 9 bytes. So of course it is not going to be, so this is much larger than the page size. So the page directory cannot fit into one page itself, right? In fact, it will take 2 to the 16 divided by 2 to the 9, 2 to the 7 is equal to 128 pages to store. So the page directory itself is going to take 128 pages, right? So for this, what we are going to do now, we divide the page directory also into different pages, and then we have another page directory, another level of page directory to do that for indexing this. So now what are we going to do? We are going to have 0 to 8 for the offset. Then, so these are the 9 bits. Then from 9 to, or 10th bit to whatever, 15th bit or 16th bit is going to be the page table index. And then 17th to 23rd bit. So again, 7 bits more. Yeah, 7 bits more is going to be the like page directory 2 or page directory 1, and then the remaining bits are going to be the page directory 0 index. So maybe this might be needed to divide again the page directory, and this will be needed because we want to divide the page table into chunks which are size of pages. Okay, so this is the main concept. You can like work out the details for this example yourselves. More details. I mean, I've tried to do it in some detail at least, just to give you an intuition how to or why this is needed. Okay, good. So these are the like basic things about multi-level page tables. There is another thing which is used sometimes, which is called inverted page table. So here, instead of having multiple page tables instead of for different processes, have one page table indexed by physical frames in the memory. And what will be the entries? Entries will be the PID of process that is using this frame, and also the virtual page number of that process, which is in this frame. So this just like reverses the picture. Now you have the memory, and all the frames are the like basically the entries of the page table indexed by that, and then the page table will have these like entries, and then it will have PID, and then it will have VPN. So it will be indexed by the frame numbers. Okay, so this is the inverted page table. And now the searching becomes like hard, because now a process is running, it gives us a VPN, and we need to find that VPN, that which physical frame it is in, like because the VPN is generated by the process. So searching is hard because like going through the whole table is expensive, and so hash tables are used to make searching fast. Yeah. So the moral of the story is that page table is just a data structure to just translate VPN into EFN, and you can change the specification as per your need.
Sir, how will hash tables help in this scenario?
So they will hash the VPNs of the of the process, and for for a certain VPN you have a hash table, and then that will point to the physical frame and so on. So I'm not exactly sure of the working of these tables, but yeah, I mean you can
Just
explore. But yeah,
just find the table in which it belongs, or inside the table the entry.
no. So there's only one table.
There is only one table.
Yeah. So in case of inverted page table, there is only one table which is indexed by the these things, the physical frames. And for every physical frame in the memory, so this is the first physical frame. And now what information we need? We need that, okay, what is the process ID of the process that occupies it? And what is the virtual page number of that process for which this frame is being used?
Okay.
Okay, there's another small thing which is, I mean, not a small thing, but if we can't keep all the page tables, pages of all page tables in memory, then we might need to put them on what is called kernel virtual memory, so that they can be swapped to disk. So we'll see like this swapping mechanism and how pages are swapped to disk and so on in coming lectures, right? So how to do swapping for pages later lectures. And these pages can be like page table pages also. So we'll like discuss it in general terms, that how do we swap pages and so on. So some mechanisms and policies for that. So yeah, that's all for today's lectures. Any questions? So yeah, we are like slightly over time, but any questions? Okay, so Monday there will be no class. It's holiday, and so I'll meet you guys on Thursday. So those who are going to celebrate Holi, happy Holi to all of you, and for those who are not, like happy holidays. Thank you.